Hello, everyone. In this part, we present the work done on estimating image depth for 3D object reconstruction in comics. I am Deplina, and I'm a PhD candidate working on said part of this project. Our goal is to assist artists in the reconfiguration of the original work to digital devices. So given an input comics panel, our methods will find the characters and objects in a comics panel, and then this will help the artist rearrange these elements in a meaningful manner. For instance, the input comics image on the left, when resized to a phone screen, squeezes the contents of the image to make them fit onto this phone screen. However, if we identify the important characters and objects in the image and then transfer them to the phone screen, we can maintain the essence of the image as intended by the artist. Here, for example, the Smurf character is kept as it is, being important in the scene, and the house is reduced in area. Note that even this relatively simple example takes roughly an hour to manually deconstruct and reconstruct. We thus automate this process. So how do we achieve this? The workflow is as follows. We first change the style of a comics image to the style of an image that we would see in the real world. We then use this translated image to find the depth of the objects. And finally, we recreate the objects in three-dimensional view using the depth information. For the sake of this presentation, let's take a look at each of these components in the following order: 3D object reconstruction, depth estimation, and finally, image translation. So what is 3D object reconstruction, you might ask? It is a process that involves capturing the appearance and shape of objects and recreating them from different positions. For example, we have multiple cameras capturing 2D images of the car from different points. The camera direction and angle gives the information to create the three-dimensional image of the car from many of its images captured by these various cameras. So let's take a look at how this really works. Given that we have this image with the known camera position looking into this three-dimensional space, we want to recreate this image as a three-dimensional object. We do so using a network which essentially works as follows. Given a pixel on the image, we can cast this ray passing through this pixel into the 3D world. We feed this 3D point into this network, which will predict the color and volume at this particular location. So we can take many such points along the ray. And we do the same to predict the color and volume for all the points along the ray, which are essentially information from the same pixel on the 2D image. Finally, this method considers all the pixels from all the frames so that the object in totality is recreated from all the viewpoints. Here are some results of 3D object reconstruction. We see that this image shows pose elevations, or poses that increase or decrease vertically. And this image shows that there are pose rotations, or the poses that increase or decrease horizontally. To obtain these results, we used depth of the objects in the image. So what is depth estimation, you might ask? Depth of an object is the distance between the object and the camera or the eye viewing it. For example, if we move forward in the scene, the depth estimates are the distance between your eyes and the object in the scene. Here, the darker colors, like purple, shows the furthest distance, whereas the lighter colors, like yellow, show the nearest distance. Note that from the distance and perspective, we get the sizes of objects. In a sense, objects nearer to your eye appear larger than the ones further away. This is an important depth cue. For the results that we show here now, we see that the depth methods, when applied to the image on the left, suffers from some challenges, such as unusual object sizes, hidden object parts, and objects that are not usually seen in the real world. As I mentioned, the method for depth estimation uses real-world knowledge, we therefore have to overcome these challenges by understanding how the appearance of objects in comics differs from those in the real world. To do so, we employ image-to-image translation, which is a method to translate the comic-styled images to the style of a real-world image. We do so using generative adversarial networks, or GANs. The GANs that are trained here are networks that generate images with real-world style, but contain objects from comics. This, ultimately, helps us to leverage models trained on real-world knowledge to improve the depth estimates. First, let me give you a general idea of what GANs are. GANs consist of a pair of neural networks that fight with each other. One is called a generator and the other one is called a discriminator, and they behave a lot like a thief and a cop. The thief is constantly trying to make fake paintings, and the cop is constantly trying to catch the thief. Note, for our work, the thief would rather make fake real-world photographs. The thief is a generator and the cop is a discriminator. So as he gets caught by the cop, the thief keeps improving and improving his photographs, making them more realistic, until one day he perfects this art and finally creates a perfect photograph that completely fools the cop. In the language of neural network, what happens is that we have a pair of networks, the generator and the discriminator, and we train them with a set of real images and a set of fake images. The discriminator is then trained to identify which images are real or which ones come from the generator. And the generator is trained to fool the discriminator into classifying these images as real ones. This excerpt is taken from the YouTube video by Serrano Academy named A Friendly Introduction to GANs. Therefore, as shown here, we are able to fairly overcome the challenges in depth estimation with the employed image translation method. If we closely look at the regions within the red boxes in the left and right depth maps, we see that the depth estimation benefits from image translation method. In summary, we show that image translation benefits depth estimation. These depth estimates, in turn, give information about size, distance, perspective of objects, helping us to understand the image, which is further used to construct three-dimensional objects that can ultimately be used to reconfigure comics images. This work was done and was funded by the Swiss National Science Foundation. And this is the team that we were so fortunate to work with. Thank you.